Chapter 17, Part 2. So the next thing is on calculating how the solubility of substance changes in the presence of other ions. So it does change when you have a solution where your substance is in a solution where a similar cation or anion is already present. This is another common ion problem. So, for example, if you have a solubility of calcium oxalate in a solution of calcium chloride, both of them are contributing the same ion. This is calcium Ca2+. And what's going to happen is a Le Chatelier's principle. So, if you have this is your overall equilibrium reaction. So if all of a sudden you increase the amount of Ca2+, it's already present from the calcium chloride, the equilibrium is going to shift to relieve that stress. It's going to shift back towards the reactants, which means you're going to have less substances dissolved and more of them whole solid. So what happens is it becomes less soluble than it would be if it was in a solution of water or a solution that didn't have a calcium or an oxalate. So, what would be the solubility of calcium oxalate in a 0.15 molarity solution of calcium chloride? So, we're looking again for this starting concentration, the molar solubility. But our initial amounts of both aren't zero. Initially, we already have some calcium in the solution from the calcium chloride, 0.15. This is going to go up by x, but now our equilibrium values are not both x, 0.15 plus x, and 0 plus x, or just x. So if we plug this into our K expression for calcium oxalate, our KSP is 2.3 times 10 to the negative 9th. Our calcium is going to be 0.15 plus x, and then our oxalate is just x. Now this plus x, you can do the same simplification as before, so we can ignore this plus x in this case and solve for x. So in this case, x is going to be equal to 1.5 times 10 to the negative 8th, which is going to be my molar solubility of my ion and a compound. So for comparison purposes, in pure water, the concentration or the molar solubility is 4.8 times 10 to the negative 5th. That's about 3,000 times less soluble when it's in a common ion solution. Okay, let's say we have lead 2 chloride. So lead 2 chloride is PbI2, not I, PbCl2. We got 2 chlorines. Okay, so the solubility, and we want to find the molar solubility or concentration, and then we can convert that to grams. Plus x plus 2x, 2x, and x. So our K expression our KSP, 1.7 times 10 to the negative 5th. We have x, we have 2x squared. So we can simplify that to 4x cubed and solve for our x. Oh, 0.016 moles per liter. So let's convert that into grams per liter. So lead is 207.2, chlorines are 35.5. So the molar mass of the whole compound, 278.2. So we can dissolve approximately 4.45 grams per liter. This is why it's so important, because lead is found in river systems of fresh water, and we can dissolve quite a bit in a liter of water. But let's say we want to do the same substance in salt waters, like ocean waters. So now, when we do our ice box, we have a common ion problem because we have chlorine already present from the NaCl. So we have 0.60, which is approximately the molarity of oceans. So this is going to go up by x, this is going to go up by 2x. So now when we plug this into our K expression, we're going to have x, we're going to have 0.60 plus 2x, and again you can ignore this plus 2x if that simplification holds true, which it does in this case. The 0.60 over 1.7 times 10 to the negative fifth, which is 35,000, so we can ignore that and solve for x this way. That's how many moles per liter. So when we change that to grams per liter, we find that there's going to be way less lead in salt water than there is in fresh water because of this common ion effect. Okay. We can also look at these reaction terms of precipitation. So instead of asking how much we can dissolve, we can ask if we mix two amounts together, are we going to all dissolve, or are we going to precipitate some of them? Have we reached the limit of how much we can dissolve? So to do this, we look at the reaction quotient Q, which we already talked about in chapter 14. And now the reaction quotient Q takes on the same form in terms of setup for solving for it, but the concentrations you put in are not the equilibrium amounts, they're the amounts that you have to start with. So in this case, my Q expression is going to take on the same form, our lead and our chlorides, but the values we plug in are not from our icebox, they're our starting amounts. And then we compare them to the established KSP values, just like we compared Q to K in chapter 14. So if Q exceeds KSP, that means we've dissolved too much, and so some will precipitate out. If it's less, that means we can dissolve more. So it will not precipitate. If they are equal, then we have dissolved as much as we can. So that's at the saturated point. But any more is going to cause precipitation. Okay. So for example, in blood plasma, we have a calcium concentration of 0.0025, and the concentration of oxalate is 1 times 10 to the negative 7th. So we do expect this to precipitate in our blood. So our Q, if we look at our reaction first, so CaC2O4. It's always a good idea to write your reaction so you know what the coefficients are, so you don't forget about those exponents. So if we plug in our concentrations from our starting amount, so calcium was 0.0025, and our oxalate is 1 times 10 to the negative 7th. Okay, so 2.5, times 10 to the negative 10th. So in this case, Q is less than K, which means it will not precipitate, which is good because we don't want chunks of things floating through our blood. It would probably be not great for our body. We could potentially dissolve more before precipitation would happen. Okay, so we have chromium hydroxide, Okay, so 1.1 grams are dissolved in 120 liters. We want to know if all of it will dissolve or not. So, all right. So what do we want to do is first we want to figure out the molarity of this. So to do that, we got to change it from grams into moles. So chromium is 52, oxygens are 16, hydrogens are 1. So we've got 6 moles per 120 liters in this case. So let's figure out what the molarity is. All right, so now when this breaks apart into our equilibrium, we're going to have a chromium. We're going to have 3 hydroxides. So we know the concentration of the chromium is going to be the same. And this is going to be 3 times as much. So I paused it and worked it out because I was running out of time for this video. So I calculated my amount of OH by multiplying my 8.92 value times 3 since I have 3 hydroxides. My Q expression is going to be written the same way. The concentration of my chromium and then the concentration of my hydroxide cubed. So we get a value for Q of 1.75 times 10 to the negative 31st. So if we compare that to what our KSP is, it is less than that. So yes, it will all dissolve. We will not precipitate any out. All right, so the last thing is the effect of pH on solubility. So you have to look at the reactions as a whole, every possible reaction that can happen for a given solution. So if you create an anion that will react with water, it can react to form your H3O+. Or you can have something that will react with water to form a conjugate base or a conjugate acid. And those things, if they form, are going to affect the pH of a given solution. So, for example, if we have this oxalate reaction, it can react with H3O+. What's going to happen with that, when this reaction proceeds, we're going to remove some of this oxalate out of solution, which is going to affect our reaction at the very top because of Le Chatelier's principle. So if we have less of this now, the reaction is going to shift to compensate, which means more of the calcium oxalate is going to dissolve as it continues to be removed through that acidic reaction. So in this case, we expect it to be more soluble in acidic solutions versus neutral solutions because it can react with this H3O+. All right, so that's the end of chapter 17. It's very short, only a few operational skills. Make sure you run through your practice problem and make sure you're comfortable working on all of these K expressions.